Okay, so I'm going to be talking about NSEC 5, which is a proposed modification to the domain name security extensions. We've been working on this project for a couple years now. So actually today I'm presenting completely new results in the sense that we've spent a lot of time implementing and optimizing this scheme. So the performance results that I'm showing you are completely different and new. And this implementation and optimization is both on the DNS side and also on the crypto side. This is joint work with a whole bunch of people, Moni at Weizmann, Dimitris previously at BU, now at Maryland, Leo at BU, Jan at CZNIC, and now at a company called NS1, and we also have collaborators at VeriSign Labs. Okay, so before we get into DNSSEC, let's talk about how DNS works. So here I am on my laptop at home, and I would like to send a query to, I would like to get data from a.com, so I need to know its IP address. So what I'm going to do is I'm going to ask the DNS for the IP address for the name a.com. The way I do this is I'm going to go send a query to my local recursive resolver. The resolver will go out to the internet, find the name server that is authoritative for the .com zone, send the a.com query to that name server, get the IP address in response, and then relay that over to me. And now I know the IP address for the a.com website, and I can go visit it, and I'm happy. Okay, so that's DNS in a second. DNSSEC focuses on the exchange between the resolver and the name server. The goal of DNSSEC is to provide integrity. So very simply speaking, we want to prevent a man in the middle from modifying the responses we get from the authoritative name server. Okay. So what is NSEC 5? So NSEC 5 deals with a very particular problem in DNSSEC. It's the denial of existence problem. So in this little picture I'm showing you, I'm going to q.bu.edu, which is a website that doesn't exist. The name doesn't exist. So what the DNS has to tell me is that this name doesn't exist. So there are various proposals for authenticated denial of existence showing that a name doesn't exist. NSEC 5 is one of them. All the other ones are standardized, by the way. This is a modification. So what NSEC 5 provides is integrity not only against man in the middle, but also if the name server itself is compromised. It also has a second property, which is the prevention of zone enumeration. I'm going to tell you what this means later in the talk. So new results that I'm going to present today, we've spent a lot of time optimizing NSEC 5. So NSEC 5, we now have it based on elliptic curves, which is a new result I'm going to talk about. We have fully specified NSEC 5. We've submitted a draft to the IETF. I'm also presenting results from implementation and performance results that Dimitris just got yesterday. So these are completely new. So before I get into the performance results, I have to tell you basically what NSEC 5 is, and in order to do that, I have to go through sort of the history of the denial of existence mechanisms used in DNSSEC. Okay, so this is the background. All right, so how does denial of existence initially done in DNSSEC? So DNSSEC has a public key that for the zone, this is known to all resolvers using DNSSEC mechanisms that we're not going to talk about today. We have our name server, we have our zone. These are the names that are present in the zone. These are NSEC records. These are the way you answer queries for names that are not in the zone. Okay, so what these NSEC records do is they take all the names in the zone, they sort them lexicographically, so you see them alphabetical order here. Then you take every consecutive pair and sign them using the secret zone signing key. So this record is signed. It can be verified using the public zone signing key. Okay. So the query comes in for q.com. We can see that this name doesn't exist in our zone, so we need to answer the query. What we're going to do is we're going to just look up the NSEC record that covers this query. You can see that q.com falls between c.com and z.com, so you know that this NSEC record proves to you that q.com is not present in the zone. Okay, so that was denial of existence in the DNSSEC, the very first version of how it worked. But if we look at what's happening here, our resolver not only learned that q.com is not present in the zone, it actually learned that, sorry, that's validating. Okay. So it also learned that c.com and z.com are present in the zone. Okay, so it's learned some additional information. It's learned that these names are in the zone. And actually, it's pretty trivial to enumerate the entire zone to identify all the names in the zone. So here he's asking a query for b.com, which comes before c.com. He's learned that a.com is in the zone. And you can see how this leads to an n query way of enumerating all n names in the zone, if there are n names in the zone. Okay? So this is not just a theoretical thing. This sort of enumeration attack is built into network reconnaissance software. You have, for example, a plugin into Nmap that will do this for you. This was enough of an issue to lead to the development of NSEC 3, which is designed to raise the bar for zone enumeration attacks. Some of the reasons given for why zone enumeration is an issue, for example, the RFCs mentioned that registries may have legal obligations to protect their zone contents. From a more technical standpoint, you can think of not wanting to expose all the names in the zone to any arbitrary person that's querying your DNS. So for instance, think about Internet of Things devices in there. You may not want to expose their addresses. You might think of a DDoS mitigation where you want to hide the names and IPs of servers so that they can't be attacked, but they still need to be in the DNS. So zone enumeration kind of thwarts all of these security mechanisms, so this could be considered an issue. So it was enough of an issue to lead to the development of NSEC 3. Okay, so here's how NSEC 3 works. We have the names in our zone. I'm now showing you how to pre-compute the NSEC 3 records. We have the names in the zone. We hash them, each one of them. So this is just the SHA-1 hash of each name. We get these 3 values. Then we sort them lexicographically. So here you see they are in alphabetical order. And then we do the same thing that we did before. We sign every pair using the zone signing key. And now we have NSEC 3 records. Okay, so these are just like NSEC records, but instead of having the names in the clear, we replace the names with their hash values. Okay? So as before, we give these NSEC 3 records to the name server, and now every time he gets a query in, he again will look up an NSEC 3 record and return it. How does he do the lookup? He takes the query, he hashes it, he gets this value here, and he looks for the NSEC 3 record that covers it. So we can see that C blah 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 falls between A blah 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 and D blah blah blah. This is the covering NSEC 3 record, and now the resolver can verify that this is the correct proof that this name does not exist in the zone because the value falls between the 2 values here, and he can validate the signature with the public zone signing key. Okay, so that's NSEC 3. So now we need to talk about zone enumeration. We can think about zone enumeration in this setting. Actually, there still is a zone enumeration attack here. This was first talked about by Bernstein. It's been implemented by lots of people. Maybe not first. Anyway, it was talked about by Bernstein, and various people have implemented this thing. So I've got this NSEC 3 record here. It's got 2 hash values here. So what my zone enumerating attacker is going to do is he's going to just collect values from NSEC 3 records. And here he can just send n online queries just to get all n hash values in the zone. So now you've got all the hash names in the zone. Now this is just a hash, so now we just do an offline dictionary attack similar to password cracking, and we reverse the hash values in the zone. Okay, so this has been implemented. Again, you can use this as part of Nmap if you want to do NSEC 3 reconnaissance for a zone. This research paper found that they could reverse 64% of the hashes in the .com with 1 GPU. So zone enumeration is still possible with NSEC 3, it's just more work. Okay. So actually, this leaves you in a problem because if you want to use DNSSEC today and you don't want to have zone enumeration at all, you have to move to online signing. Okay, so what online signing does is it changes what's happening here. Previously, our name server had pre-computed records that it was just using to respond to queries. What we're now going to do is we're going to give the zone signing key to the name server, which by the way means that if the name server is compromised, the entire security of the zone is gone. Okay? But in any case, you give the key to the name server, and now whenever a query comes in, you're going to compute an NSEC 3 record on the fly. So I'm just going to hash the value, here's the hash, and I'm just going to take +1 and -1 of this hash value and generate an NSEC 3 record that contains those 2 values. So you can see that this value here falls between these 2 values, and now we know that this is a covering NSEC 3 record for the query that was generated on the fly. And this is great. We don't have zone enumeration because these hash values are independent of any names that are actually in the zone. They just depend on the query. Okay, so this is how we do the prevention of zone enumeration now with DNSSEC. Okay, so just to go over, these are the different schemes that we have. We have legacy DNS, which never had a zone enumeration problem before. With legacy DNS, if you'd like to learn the names in the zone, you need to send an online query for every name you suspect is in the zone. That was the state of the world with DNS. But of course, there was no integrity. So there was no authentication no signatures on the messages, so a man in the middle could tamper with the messages. Then we have NSEC 3, which has this offline zone enumeration through the dictionary attack that we talked about. So you can make n online queries and then do offline zone dictionary attacks to recover the names in the zone. But it does provide integrity against a man in the middle. And then we have online signing, which doesn't have this offline zone enumeration problem and doesn't have a problem with outsider attacks, right? But in this case, you have to do an online cryptographic signature and give the zone signing key to the name server. Okay, so I have 2 things to say about that. We can see the downside of online signing is that the secret key has to go to the name server, so if the name server is compromised, the integrity of the zone is lost. And another thing is, in a paper from a couple years ago, we proved that any scheme that both prevents offline zone enumeration and provides integrity against outsiders must necessarily perform one online public key crypto operation per negative response. So in a sense, online signing, the fact that we are doing online crypto here, we do need to do online crypto in order to have both of these properties. And this is sort of why we see the state of the world like this. Okay, so what does NSEC 5 do? NSEC 5 prevents offline zone enumeration without having to give up integrity when the name server is compromised. Okay, so that's the trick that we use in NSEC 5, and now I'm going to show you why this works. And just, I wanted to note that in order to do this, we do have to perform a public key operation, not a signature, but a public key operation for every negative response. This is necessary. We showed it in this theorem. Okay, so now let me show you how NSEC 5 works. Okay, so just revisiting, why was zone enumeration possible with NSEC 3? The reason was our attacker just collects all the hashes in the zone, which he can do with n-queries, and then he cracks them. And the reason he can crack them is because he can compute hashes offline by himself. Okay, so he can hash by himself. That's the crux of the issue. So what we're going to do in NSEC 5 is we're going to get rid of this hash function, which was what was used in NSEC 3, and we're going to use a new kind of quote-unquote hash function, which is a verifiable random function. So for cryptographers, most of us are cryptographers, maybe you've seen this before. This is basically like a keyed version of a hash function, but it's a public key version of the hash function. So there's a secret key that's used to compute the hash and a public key that's used to validate that the hash is correct. Okay, so this is what we're going to use in NSEC 5. Okay, so here's how it goes. We have our names in the zone, and now we're going to hash them, quote unquote, with the VRF, with the verifiable random function. This hash uses a secret key, which is the secret key of the VRF. Okay, so here's basically what my hash is. I'm going to take the name, I'm going to do something to it with the secret key, and I'm going to get a value. In a second, I'll tell you what I'm going to do to it. I'm going to do this for each one of the names. This should look familiar. This is exactly what we did with NSEC 3. So we do a VRF computation on each name. We get all these values. We sort them. And then we sign them using, we lexicographically sort them, and then we sign every pair using the zone signing key. So we get these NSEC 5 records. Okay, so this is exactly the same as before, except instead of using SHA-1 here, we use the VRF. Okay, so what is this VRF? So the first version of NSEC 5 that we presented a couple of years ago, this VRF was based on RSA. So in this VRF, the pi function here was basically a deterministic RSA signature. So it was a full domain hash RSA signature. And this hash function here was just SHA-256. Okay, so we basically take an RSA signature, apply SHA-256 to it, and that gives us our VRF output. Okay, the new version of NSEC 5 that we're going to talk about now, I'm actually not going to show you the crypto behind it, but the crypto comes from this paper by Franklin and Zhang. Actually, the construction appeared in there. It wasn't supposed to be a VRF, it was being used for something else, so we proved it's a VRF. And actually, this construction turns out to be much more performant than the RSA construction. I'll show you the performance results in later slides. So in that construction, this pi is an elliptic curve. Uses elliptic curves. I'm not going to tell you more about it than that. Okay, so that's our VRF. So here's our NSEC 5 records that we pre-computed, and now we give them to the name server. Okay, notice that I have not given the name server the secret zone signing key. However, we do have a VRF key that we have to give. So first of all, the VRF comes with a public key that everybody learns using the usual DNSSEC mechanisms. And then there's also a secret key for the VRF, and that's what we're going to be giving to our name server. So the secret VRF key is given to this guy here. In a second, I'm going to tell you why this is okay, but for now, let's just talk about what we're going to do with this thing. Okay, so how does NSEC 5 work? When a query comes in, the name server needs to figure out what NSEC 5 record it has to deliver to the querier. So how is he going to do that? Well, he has to basically quote-unquote hash the query. So he has to compute the VRF value. So the first thing he's going to do is he's going to take this pi function, apply it to the name, and get this value. That's using the secret VRF key. Then he's going to hash this output. And then he's going to get this value here. This value is, now he's just going to look up the NSEC 5 record that covers this value. So you can see that 3 blah, blah, blah comes before 7, and then 8 comes after. So this NSEC 5 record covers this value here, and now he delivers it to the resolver. Okay? So at this point, you should say, wait a minute, how can you verify this thing? Right? Because the resolver cannot compute this hash value on its own. How is he going to verify this? So what we do in NSEC 5 is we provide an additional piece of information which is called the NSEC 5 proof. The NSEC 5 proof is just the output of the pi function. So we take the output of the pi function and we send it along with the NSEC 5 record. Okay? So the name server computes this thing, sends it along, and again, in our RSA version, this is just an RSA signature. We send this along, and then to verify, we have 2 steps. The first thing we do is we check that the NSEC5 covers the proof, so we just hash this value and check that it falls between these 2 values. Then the next thing we do is we check that the proof and the query actually match. So again, in the RSA version, the proof is just an RSA signature on q.com. So this amounts to an RSA verification. So we take the query, we take the proof, we verify them, and if they match, we know that these match. And of course, we verify the signature on the NSEC5 record, and now we know that this name doesn't exist in the zone. Okay, so that's NSEC5. We have to give a proof record. We have additional keys, which is specifically used for NSEC5. And we have to do this online computation in order to respond to the query. Okay? The online computation, by the way, is comparable to what you do in online signing today in order to avoid zone enumeration. They also have to do an online computation. Okay, so to compare these different schemes, why does NSEC5 prevent zone enumeration? Very quickly, we cannot compute VRF hashes on our own. So that means that the zone enumerator cannot actually do these offline dictionary attacks because he can't hash by himself. We do need to perform an online crypto operation when responding to a query, but this is necessary by the theorem that we proved. And finally, I need to tell you why this provides integrity, and that's what I'm going to do next. So here's my proof of why NSEC5 provides integrity, even if the name server is compromised. Okay, so here's our attacker. He's compromised the name server. He stole the key. So now he has this key, and he needs to convince us that something is not in the zone even when it is. That would be an attack, right? So I'm going to ask for a.com, and he's going to tell me, no, this doesn't exist in the zone. That's what he's trying to do. He's trying to give me the wrong answer. As you can see, a does exist in this zone. All right, so here's what he's going to do. First thing he's going to do is he's going to compute a proof record. Actually, this is totally easy for him to do because he has the VRF key, and he can compute the proof on his own. Remember, this is just basically in the RSA version. It's an RSA signature on the query. So he can produce this proof on his own. The important thing is that the VRF has this property that the proof, at least the RSA VRF, and this follows to the other VRF as well, the proof value here is going to be unique given the query and the public key. Okay, so there's only one value that could possibly appear here. And so this value better be correct also because the verifier is going to use the VRF key to verify the proof. So this proof value is actually the correct proof value. Okay? So now our attacker needs to give us NSEC5 records that convince us that a.com is not in the zone. But he doesn't know the zone signing key, the secret key, because it's not given to the name server, so he can't forge NSEC5 records. So he has to replay them. Okay, but now if we look at the NSEC5 records he has available, actually none of them are going to work in terms of replay. This one doesn't work. It doesn't cover the hash of the proof value, which starts with 9. This one doesn't cover it if actually it matches it. This one doesn't cover it, it matches it. And so none of these records work. There's nothing to replay. And that's why integrity is preserved even if the name server is compromised and the VRF key is leaked. Okay, so that's how we get the security of NSEC5. And if you think about it, this is exactly why NSEC3 is secure. If you just get rid of the VRF and just think of SHA-1, this is exactly why it works. Okay, it's the same idea. Okay, so I just showed you why we have integrity, even if the name server is compromised. And so this is kind of the state of the world. These are the options. You can have offline zone enumeration, be robust to name server compromise, but not do online crypto. Okay, so if you don't care about zone enumeration, this is a good solution. If you care about zone enumeration, in this solution, you lose integrity if the name server is compromised and you have to do online crypto, versus NSEC5, where you do not lose integrity if the name server is compromised and you also have to do online crypto. Okay? So that's basically the state of the world. And now I want to show you some of our new performance results. So we've actually gone and implemented NSEC5. Our implementation extends existing DNS commercially available open source software. So our name server implementation uses not DNS and our recursive uses Unbound. We have both versions of NSEC5 implemented, the RSA version from our first paper and then this new elliptic curve version. I'm going to show you that this version is more performant in a second. Also, some really cool things that we incorporated in the new version is that we looked at some optimizations that the DNS community developed for NSEC3, but they were actually developed after NSEC3 were standardized, so they were never actually used. So we actually are able to incorporate these optimizations into NSEC5, and that gives us a much better performance. I'm not going to talk too much more about these. I can talk about this offline. So 9,000 lines of code. We used OpenSSL, which was already inside these implementations, so there's no new dependencies. We didn't really need any new crypto. We just used the crypto that was in these. And also, the optimizations that I'm talking about are all protocol-level optimizations. We did not do systems-level optimizations here. This is just extensions of existing implementations. Okay, so the first thing that I want to show you is the length of the responses. So let me just read to you this chart, and then I'll tell you why we care about this. So this is the response length in bytes. This is the length of an internet packet. And these are different versions. This is NSEC3 using RSA, NSEC3 using ECDSA. This is NSEC3 online signing using ECDSA, so these things are roughly the same. NSEC5 using RSA, and NSEC5 elliptic curves. Okay? So first of all, why do we care about response lengths with DNSSEC? There's two reasons for this. First of all, in DNS, when you send a query, it goes over UDP, and you want the response to fit in a single packet, because if it doesn't, either the packet gets fragmented and bad stuff happens, or you have to redo the query over TCP, which adds more latency. So it's really nice if your response fits in a single packet. We can see that our RSA version of NSEC5 actually did not. The 2048 version of NSEC5 also doesn't fit into, NSEC3 doesn't really fit into a single IP packet either. So these are bad things. But when we move to elliptic curves, you can see that NSEC3 does, and NSEC5 also does. And in fact, that the NSEC5 based on elliptic curves in terms of length is roughly comparable to NSEC3 based on elliptic curves. Okay, so this comes from the fact that we've done the elliptic curves optimizations and also the DNS optimizations. The other reason why we care about this is actually because the DNS can be used as an amplifier for distributed denial of service attacks. You can imagine an attacker spoofing the IP address of a victim, sending a query to the name server, and the name server responds to the victim. If that response is really, really big, then the victim, the rate of packets going to the victim gets higher. The rate of bits going to the victim gets higher, and that's bad. So we don't want to blow up the length of responses. So that's another reason why response length matters. Okay, so when we do NSEC5 with elliptic curves, we're actually not losing much in terms of response length relative to NSEC3. Okay, and this is based on our implementation. Actually, the other thing I wanted to say is that today most of the DNSSEC uses RSA 1024, not 2048. So this is what response lengths look like basically on many implementations now, many deployments now. We can see that moving to elliptic curve NSEC5 is actually shorter than what's currently being done in the deployments. Okay, the last thing I want to show is the throughput of our name server. So what we did here was we set up a name server, and when I say we, I mean Dimitris and Shuman. So there were 24 threads running on 40 virtual CPUs. So this was a big box, what you might imagine acting as a DNS server. What we do is we send queries to this box at a steady rate. You can see we started at 8,000 queries per second up to 128,000 queries per second, and we see when the box can no longer respond, basically where it maxes out. Okay, so this line here is the NSEC3 line. Remember that NSEC3, you actually don't have to do any online crypto. You just have to do a hash and a lookup. So this scales basically perfectly, but this is a log-log scale, so this line is linear. Okay, so NSEC3 has no problem scaling. But when you start to turn on online signing, this is an online signing implementation from PowerDNS. This is, by the way, everything here that you're seeing other than this purple line is not DNS. The reason we use PowerDNS is because PowerDNS was the only open source RFC compliant thing that we could find that was doing online signing. So we used that in the evaluation. We can see that online signing with PowerDNS is maxing out around, I think, 21,000 queries per second. Our RSA implementation of NSEC5 maxes out similarly around like 19,000 queries per second. If we look at our NSEC5 elliptic curves implementation, we're maxing out at 64,000 queries per second. So we're pretty excited about this result. I still can't really put this into context because this is from yesterday, this figure. And one thing that we did do is we looked at the average query rate at the root, and that is about an order of magnitude lower than this on average. So we think that these numbers are pretty good. I'm happy to talk more about what these numbers mean. Again, they're really new. So this is an ongoing project. We are continuing to do performance analysis, so we haven't tested the resolver performance yet. We have to do that. We're also going to use captured traces as opposed to these synthetic queries that were coming in at steady rate that I've shown you. We have an internet draft. We're hoping to get this included into the DNSSEC specs, and the implementation is publicly available. So with that, I'll stop. These are some memes that we didn't make. We just found on this website. So thank you.
So we do have time for questions, so let's go right ahead.
Thanks, really nice talk. So I have two questions. One, the obvious question is, what happened to 4?
What happened to 2 as well, actually?
Yeah. But the real question is, so you talked about replay and how replaying doesn't work, but how do you prevent replays from a previous time when there really wasn't an A.com?
Yes. Okay, so that's kind of not my problem in a sense, because that DNSSEC has this problem anyway. So the question is, how do I prevent stale records from being replayed? So DNS, honestly, I can't answer this question very well, because there are all these mechanisms like TTL that are being used and figuring out exactly what the right TTL is and when you should expire your signatures to make sure that things are expired before you add the new data. So anything that's dealt with in that way in DNSSEC, we just like drop into our scheme here. So I don't really have a better answer than that.
NSEC records have time limits.
Right.
Least and largest for which they're bound.
Right.
Okay.
Right.
Thank you.
So Trevor Perrin has a very fast and simpler VRF called VXEdDSA. Did you consider using any other VRF, or would you consider that for? I
didn't know about that. That's really interesting. So I'd love to look more into that. Maybe it's even the same VRF. I don't know. Yeah, I'd be very interested to see.
I don't know which one you're using exactly. But
yeah, it's one that we proved was a VRF, so it may end up being the same thing.
Could be.
Okay, thank you.
Hi, my name is Victor Duchovny. I work on Dana Bunch. Depends on DNSSEC. I'm not sure if this is exactly a question or a comment, but for many domains, the highest risk is operational more than crypto. People forget to redo their offline signing and their domain disappears off the internet. So for folks without very strong operational discipline and support teams and so on, actually having the key present on the name server is important so that you can keep signing. Right, so the DNSSEC became a lot more reliable once bind implemented auto-maintain, and people could leave their keys online and have the name server automatically re-sign. I understand, of course, the roots and .com and so on have ways of doing offline signing reliably, but for the sort of average, much smaller domain, the keys do have to be online, because otherwise the risk of going dark is much higher than any risk from compromise. So that's sort of a trade-off that people have to be aware of, in that offline signing is cool, but most people can't do it reliably. I think that's all I have to say for the moment.
Okay, I guess I just wanted to say to that, I take that point. I think just what we, can I get my slide back up, please? Sorry. I just wanted to point out that in the case where you want all of these things, this is the way that we're proposing that it will be done, right? So again, if you don't care about zone enumeration, then you shouldn't be doing this. But if you do, then this is the way to do it. Okay. Thank you.
All right, so let's thank Sharon again.